Welcome back to this 31-part series. We are about to do a two-part little mini series within it. This is the chemistry of indoor environments. Again, this is a huge, sprawling 10-year study. And these two parts that we're going to do are panel discussions. So this first one is all going to be about health effects and exposure risk, the public health end of this thing. This is going to be, I think, a pretty interesting conversation. I hope for you. It is for me. Part two that follows this will be all about ventilation and kind of the technology and what works and what doesn't. I'm going to take a break from being your moderator because this is the discussion and it's a lot more plain English. It should be unnecessary for me to explain anything at all. Here we go into the health aspect of this.
Well, hello, everyone. So I'm Crystal Pollitt. I'm from the Yale School of Public Health, and I'm so happy, to be invited to this. Thank you for bringing everyone together from such a range of different disciplines, and now shifting the conversation to be talking not only about indoor chemistry, but now this intersection between exposure and health. And this is really where my area of interest comes in, thinking about how we can evaluate personal exposure to all the different types of chemicals that we are exposed to, and especially those that we're exposed to in indoor spaces. So much of my work is focused on wearable passive technologies that we can then couple with high resolution mass technologies to be able to then understand the range of different chemical constituents to which we're exposed to. So with this session, we have three fantastic panelists that I'll invite to come up onto the stage. We have Antonio Calafat from the CDC. We have Jim Zhang from Duke University, as well as Elena Jaspers from UNC. So I'd like you to come up onto the stage. And as they're coming up, I'll go through how this panel session will take place. So we'll start off by allowing each one of our panelists to share some background about their work. So we're going to shift gears and they're going to talk about how they evaluate exposures, how they evaluate health, what is important for them, where do they see this intersect between everything we've been talking about before with chemistries coming together. And then we'll open it up to everyone else to ask questions. And I'll also have my laptop here so that we can then see if there's any questions coming in from the webinar as well.
Yes, my name is Elena Jaspers. I'm from UNC Chapel Hill. First of all, Glenn, thank you so much for inviting me. This has been a tremendous experience already. My training is in inhalation toxicology. And I received my training at New York University. And actually, as a matter of fact, my dissertation was on ozone, outdoor ozone. And so we studied the health effects of ozone, not so much in the indoor environment. I'm professor in pediatrics, environmental science and engineering at UNC. I also run the Center for Environmental Medicine, Asthma and Lung Biology, lots of different hats. But bottom line is we're all interested in the health effects of anything anybody can inhale. These are ambient air pollutants. These are products such as cigarettes, e-cigarettes, vaping devices, all kinds of things. But we're really interested in the various health effects, respiratory, cardiovascular, immune, systemic effects that these inhaled exposures cause. The mechanisms or the systems we use to study this are both human exposures. So I was really excited to see some of the wildfire studies that were just presented here. So we actually do controlled human exposures to wood smoke. We do controlled human exposures to ozone, NO2, as well as other, in collaboration with EPA. We also do some more reductionist approaches. And we're also now moving into the field where we're trying to get very non-invasive sampling of humans exposed to various pollutants. So that's a nutshell. I do both in vitro toxicology as well as human clinical studies. I usually don't do animals. I don't do the four-legged animals, but I do the two-legged animals. But other than that, we're doing a lot of different human exposures and human investigation on the translational continuum.
My name is Antonia Calafat. I work at the Centers for Disease Control and Prevention. And before starting, I want to thank Glenn for the opportunity to come and speak to all of you. Is kind of a different audience than the one that I'm used to talk to. So I hope that what we because again, I work mainly in exposure and looking at health effects. So something that hopefully will interest you. I'm a chemist by training. I got my degrees in Spain. I came as a Fulbright scholar for 2 years, and he's been 34. So you can, I have devoted most of my career at CDC, and I work in a division of about 450 people. Most of us are chemists. And we are in the business of evaluating exposures to chemicals by measuring the concentrations of those chemicals or their metabolites or background or breakdown products in urine or in blood mainly. So we look at what we call internal dose. So because we believe that if there's no exposure, there's going to be no hazard, at least for human health. So we are lucky enough to have a suite of different mass spectrometers. We do our characterization by mass spectrometry, and we look at about over 400 chemicals. I know it's only a fraction of the thousands of chemicals that are in the environment, but at least this is a start. And in this suite of chemicals, we covered essential elements and metals, as well as organic compounds, which is what I have devoted most of my life, including volatiles and semi-volatiles that have been mentioned today. We do look at VOCs. We look at PBDs, polybrominated diphenyl ethers. Those are flame retardants. Some of the chlorinated flame retardants, somebody asked about that. So those are contemporary flame retardants, phthalates. Some of the PFASs, they were also mentioned, and pHs. And I think I even saw DEET, so an insect repellent, a pesticide. We develop analytical methods for measuring concentrations of chemical biomarkers in people and apply those methods into a very large survey, the National Health and Nutrition Examination Survey, conducted by CDC on an annual basis. And we measure concentrations of these various chemicals within what is the general US population. All our data are public, and they're reported either on the Enhanced website, the raw data, or in the form of tables in what we call the National Report on Human Exposure to Environmental Chemicals. We also work with a large number of investigators. I have worked with some of you, but very few. And in looking at the effects of exposure, as well as into characterizing sources of exposure. From the measurement in blood or in urine, we know that exposure occurred, but we do not know what was the source or when did it happen. So we partner with other investigators to better understand the sources of exposure, because I work at CDC is in order to prevent exposure for further producing health effects. And we have done some studies that maybe can resonate with you in terms of chambers. I mean, and now it's like controlled chamber studies in which we looked at exposures to pesticides in the military by wearing their uniform that had been impregnated with pesticides, and looking in the chambers at how is the impact in exposure based on changes in humidity, temperature, time, and so on. We also have done some work with NIOSH investigators in looking at exposures in firefighters from controlled exposures. So during training, when they train firefighters, and then evaluating the exposures looking at the concentrations and determining how exposures happen. And I think that in a nutshell, this is what we actually do at CDC. Thank you.
My name is Jung Fan Jan. My friends, I call me Jim. So I think a little bit easier. Thank you for this opportunity. And I was trained as a chemist to start with. I always say I'm a chemist. I had a bachelor degree in chemistry and master degree in atmospheric chemistry. My PhD is in environmental science and public health at Rutgers. That was a long time ago. And my PhD dissertation work was actually inspired by the 1991 and 1992 papers that Bill and Charlie published on the ozone chemistry. So I did my dissertation work on indoor aldehydes formations from ozone reaction that sort of thing, measured the homes, and 6 homes in New Jersey. That was in 1994, whatever. So I stay interested in the indoor air chemistry, but my research funding started, I would say, 1999 or whatever, is mostly NIH. So you know that NIH doesn't really fund indoor air chemistry kind of work that's shown here. But so, you know, it's epidemiology, toxicology, clinical trials, that kind of work. So anyway, but that was about 2 years ago. I was doing my sabbatical at DTU with Gabriel Powell, and Charlie came to spend his 2-month time over there. And of course, that's a great time, you know, to think back about the ozone chemistry work again. And really, you know, Gabriel Powell, of course, I'm sure you always think about what's the health implications of those chemical reaction indoors, right? So that, I think Charlie and I had chatted about some existing cohort data sets I have. Again, those are the intervention trials indoors to reduce PM 2.5 concentration, look into health improvements, right? Or just a panel study look into exposure relationship with the various health outcomes. So with that, you know, we have never thought about or never proposed to say, what is the ozone reaction product that produced indoors, what kind of health impact that is. So we went back to 2 of my old data sets. I did some analysis, use ozone loss, which is outdoor ozone level concentration minus indoor ozone concentration, as the proxy of ozone reaction products, that associate that with the pathophysiological indicators, somewhat has clinical relevance, some molecular level indicators of the cardiovascular and respiratory health outcomes. So I have one slide, if that can be easily pull out. Here you go. So here is just the one, this is in 43 children with the asthma. So we did work in, I can see familiar. You can see that the x-axis is the percent change in those various biomarkers. Those are indicative of oxidative stress, inflammatory pulmonary inflammation, FeNO, and also the airway resistance things that indicative of how easy a person can breathe. For people with asthma, that's critically important. If you increase kind of a little bit of airway resistance, that means those, the people would have more difficulty to breathe. So anyway, you can see that if we do the ozone, this is personal ozone exposure. We measure indoor ozone levels. We measure outdoors. In some cases, if we don't, we use the central monitor, and then we have a time activity, and then that calculate that personal ozone exposure for 12 hours, 25 hours, different time, averaging time. Other than that, as I said, we use the ozone loss as a proxy for ozone reaction products. So the red showing that's the change of percent change of each of those health outcome indicators per unit change of either ozone, that's the blue dots a blue line, and the red line is the change per unit change of ozone loss. And you can clearly see here, looking into that adverse effect side, so increases or some decreases, whatever. So the changes into the worsening direction, you can see more biomarkers are related to ozone loss and than the ozone itself. We reproduced the similar results in adult cohort, and we have, my former student Lin Chen went back to work on a lot of data set. Again, this was project finished many years ago. The data sets were there. We were able to reproduce that in another one, which just got the results 2 days ago. So anyway, this is really showing that there's the the stuff that people are doing, the intermediates, whatever, those very detailed chemistry do have a potential for health implications. So I will stop there.
Okay, so thank you for the overview. So now if we step back and think about what are sources, what are different chemicals that you think that would be of interest to you to move forward and study? What is the level of evidence that we have for contaminants indoors that have been studied? And what approaches do you think that we need, or questions that you have for the audience that have presented on indoor chemistry?
There's some of the evidence that really has sparked quite a bit of discussion in the sort of respiratory health field is evidence showing that NOx, in particular NO2 from cook stoves, from gas cook stoves, is associated with the development and exacerbation of asthma. So we already know that if you look for a specific chemical, you can make the linkage. And obviously what you demonstrated is sort of like in that line. So, but that's a single one. So I think sort of taking a bigger approach and more complex mixture approach in terms of what are other, like NO2 may just be a proxy for something else. Like you already indicated the loss of ozone may be the proxy of something else. So I think we need to sort of take that momentum that we currently have with the understanding that indoor air pollution does have significant health outcomes, but taking it to the next level and looking at more complex mixtures, off-gassing for like brominated flame retardants, things like that. All the interaction that we have, with the environment as an indoor, the skin oils. I mean, I've been fascinating with that. I think we need to take that to the next level and sort of combine maybe some of the sort of controlled houses that have been built and put humans in there and study them, or put sort of any kind of biological experimental system to see whether that actually can link the detailed chemistry that is sort of now being studied from the indoor air, but linking it to more defined biological outcomes, because we already have evidence it is happening.
Much to add in there, but I must admit that I have always been thinking about like the indoor environment. I mean, obviously, at least in the United States, then most of our exposures, if you accept diet, then they're going to come from the indoor environment, being in your office, at home, in your car. And then because we mostly live in buildings that are sealed, the air is recirculated over and over again, and we spend little time outdoors. I mean, certainly not in Atlanta during the summer. So you're most of the time indoors rather than outdoors. And I had always been thinking about, again, we're looking at exposure and how lifestyle influences your exposure. Certainly lifestyle and certain demographic characteristics, your socioeconomic status is going to affect tremendously the type of exposures that you're going to be experiencing. And this is something that we're looking a lot now, how, certain type of housing may just exacerbate exposure to certain chemicals. We think about how tobacco smoke can infiltrate, areas, but you think about any other type of chemicals or other type of exposure that may be in an apartment building, like that they're going to be, like just is not only that there's nothing specific about tobacco except that there is a gas, and then so anything else is going to be circulating around too. So we're always interested in looking at how exposome, if you want, which is a word that you perhaps have heard, can affect health. And it's very important to consider that up to now, a lot of the work has been done on a chemical by chemical basis. Even in epidemiology, there have been, exposure to X causes this, exposure to chemical Y. well, we are really exposed to like a large number of chemicals, and your data beautifully showed it. And one thing that I had not appreciated until today, to tell you the truth, was that, I was thinking, yeah, you put, personal care products, and then you apply them, and then you knowingly are using a product that is going to expose you to certain chemicals. What I actually had not thought about was that you are also like a source for the chemicals outside, because then, like within the air, the chemistry is going to be interacting with you and everything that you're using. And then, so you're not only the recipient, but also a source. And I should have known this, because in the lab, we have had cases of contamination that turned out because somebody just switched the toothpaste, and suddenly that toothpaste had a chemical that was one of the ones that we were looking at. Or somebody, like they changed the cream, and then suddenly we were having the sunscreen agents were off the roof only with one person. I mean, nobody else in the lab. So I should have thought about it, but I didn't. So thank you for bringing this. I mean, and as far as how we can move forward, I think that perhaps it's possible in your program to also add the human component, and then consider how biomonitoring, which is only one of the tools, could complement the data that you're having from what you're having in the air. That could give us the perfect picture of exposure. And again, I would say again, there's no exposure, there's no hazard.
I can't agree more. The only thing I think I'd like to add at this point is this climate change, changing environment, especially changing indoor environment. From what we hear, we learn from this program and the other publications is the ventilation rate, the air change rate, the climate control of the indoor environment has profound impact on those, that does translate into the chemical residence time indoors. So affects all those, the reaction, that sort of thing. So that would really affect the exposure, right? The profile, it's not just concentration, and also the speciation of the mixture. So what does that mean to the health? I think, for me, as a researcher, I need to get my research project funded. And I've been always chasing money from NIH. They do have this climate health impact with lots of money, looking for all kinds of research. Some ideas are good, some are not that good, but they got funded because it's very timely, whatever. I've been on the review committee, all those things. So, but it really the climate impact on people's daily living, which is, we all know that 90% of time we spend indoors. There's none of those kind of proposals come in. So anyway, I've been, thinking how we can take this opportunity to really address the exposure to indoor environmental chemicals and other stuff, maybe biologicals as well, and in the changing, attribute to climate change, and then how we can address that.
That motivation to set some potential collaborations for some future NIH proposals incorporating health and chemistry and exposure. So on that note, I'd like to open it up to the audience if there's any questions. If you'd like to go up to one of the two microphones.
Hi, I'll start. I'm Grace Lunsford, and you'll see a video after lunch. I've been filming many of these scientists and their amazing work over the last 5 years. And my job is a bit of a translator. And because it is on YouTube and through our PBS television show, we have people coming to us every single day with multiple chemical sensitivities, realizing that autoimmune disease is now possibly coming from their home because they moved and all of a sudden everything has changed. And so there are two things that I'm curious about. One, how can I help direct these people into studies, into opportunities, who are literally going through it and who are seeking me out? How can I help them get to you? And secondly, this is probably as a woman approaching 40s and also having two little girls, I'm really curious about hormones and the hormone interaction with the chemicals that are happening. And I'm wondering if you're seeing more interest around those studies, especially the bisphenols. There was a lovely poster last night about that. And so I know some of you guys are doing that work, but it's definitely top of mind. Thank you.
Questions and great points. And thank you so much for translating to people that need to hear about it. I'm a big fan of that. So to maybe get to the second part of your question first in terms of hormones, and the NIH now requires all of us to address sex as a biological variable. So we can no longer do studies in just male mice or males between the ages of 18 and 20. No, that it doesn't work anymore. So many clinical trials failed because I am not, an older version of an 18-year-old boy. I'm not. Most of us are not. I have one of those at home, and I can guarantee you I'm not. So I think we all appreciate that hormones over the lifespan, prepubescent, puberty, adulthood, menopausal, postmenopausal, all of those changes completely the biology in their interaction. And there is a big push in terms of also understanding endocrine disruptors. So phthalates obviously are some of them. They're mostly studied in the context of oral exposure. So I think what you're bringing up is a really interesting point. I had never thought of endocrine disruptors necessarily in the inhalational exposure. So I think that's a potential knowledge gap. So hormones do play a big role. We need to understand better how some of these chemicals, disrupt our hormones in a body, because there is now a change in puberty potentially because of these endocrine disruptors. But at the same time, also, how do some of these endocrine disruptors modify immune health? Because you talked about a lot of these sort of immune disruptions. How can we help these people? That's a great question. I don't know. I mean, obviously, studying them, maybe recording them, publishing case reports is a big deal. So if there is a documented change in environment, and then like the occurrence of a new disease, those need to be documented, because if there's enough of those, it becomes a bigger study, and sort of like a cause for more cause and effect relationship analyses.
For your point, I'll start with the first one, and how can people get to where research is being done? I really cannot speak for academia because I work for the government, and we work with people in academia, but they're the ones who design the studies, and then they're the ones who, recruit participants. So we do not have an interaction with a study participant. There are certain studies that we participate that are studies in communities. Then there again, generally they're either government, they're all government funded for the most part. Some are with foundations, but just very few. And I would just say, I really do not have an answer, but perhaps to look into it, there's certain concerns. They may be looking into some of the, can look certainly at CDC, can look at ATSDR, the Agency for Toxic Substances, and Disease Registry is a partner agency or a sister agency, I would say, of CDC, looking at some environmental groups that they have very good information about some contacts, if you want, that people can just go and try to get in, being part of a study. In terms of, hormones, then yes, it's very true. Many of the chemicals that we're looking at, they're chemicals, and hormones are chemicals too. So it's just, and then many of them can have, many of the chemicals that we're looking at, and some of the ones that you're looking at too, they have some endocrine disruptors. They can mimic the regular or the natural hormones in the body. And, the body is really not used to, is not prepared for these xenobiotics. So we're trying to get rid of them. That's why we can take advantage of this and measure some of those chemicals or the breakdown products in the urine. Like you're supposed to phthalate. The body doesn't want the phthalate in the system. So it's just going to metabolize it and trying to get rid of it quickly. So that's why we can take advantage of look at some of these chemicals in excretion products. But there's more and more evidence now with epidemiological research suggesting that exposure to some of these endocrine disruptors have some effects with health. And again, just think about that is not only one particular chemical, but all this suite of chemicals. And also importantly is the time when those exposures may happen. It's also very clear that now certain times in your life when exposures may be potentially more harmful than at other times. So, early in life, during adolescence, and then, in reproductive years for women, obviously, and then even later in life for some of the very different diseases that may not have to do with your reproductive health, but your mental health. So, these chemicals are going throughout the whole life cycle, and many of them do have the ability to interact with the hormonal system.
Okay. Lou Harriman, now retired, formerly Mason Grant Consulting, and most of my background has been on the HVAC side and on the humidity control and the moisture effects of that. And what I'm trying to do is understand, your reactions to some of the data that we've seen this morning in a little bit more detail. So one specific question for you, Jim, if I could, just to make sure that I understood that right. So we're looking at that graph that you showed us, the one that you put up there. That's so for a 10 part per billion increase in ozone, you had between a 60 and 100% increase in oxidative markers for oxidative stress. Did I understand that properly?
Yes, I couldn't see it clearly, but whatever you read is
Okay.
Yes, correct. It was 10 ppb increase in ozone loss percentage in change in the markers. Yeah.
Okay. So now when you look at the other data that was presented from our other presenters earlier today about the increases and the rise and fall of ozone as a result of different phenomena that we've been talking about here, does all this say, holy Christmas, we're in big trouble? Or is it like, well, that's kind of interesting. It's kind of small. And I'm interested in your reaction, Jim, and also ladies, your reaction too, if I could get that.
So some of those molecular markers, there is no clinical benchmark. So let's see, a oxidative stress marker like malondialdehyde or 8-hydroxy deguanosine, deoxyguanosine. So we know that increase is not good. But for fractional exhaled nitric oxide, as phenol, clinically, they said 20% increase is bad, 20% decrease is clinically if they use treatment, that would be okay. So I really didn't look into my data set of the real data, but 10 ppb it's a real change, right? So if a 10 ppb increase in ozone concentration at 10 ppb increase in ozone loss, actually, Charlie at the below you published a paper sort of doing the stoichiometry, right? About one molecule ozone loss is equivalent to how many molecules of the ozone reaction product, average kind of thing. So maybe you can put it in. But anyway, the 10 is real, and then if a 20% change in phenol clinically is important. For asthmatics, that's already, you see that clinical relevance. For the spirometry, like FEV1, FVC, those things, 4% change for asthmatic for COPD, that's quite clinically significant. They don't have that big a change, but the airway resistance, those things, again, no clinical benchmark, but the direction would change is very clear.
Significant.
Yeah, it's very clear.
Other thoughts from our other panelists on those numbers and their implications?
So I'll start by saying I'm not an expert in ozone or an air pollution indoor or outdoor person, and I'm not a clinician either. So I really cannot comment on that. But I would just say that from a public health perspective, and again, CDC is a public health agency, we are interested in looking at the population health, if you want. So there are some changes that they may not be relevant, and they may not have a clinical difference. So, maybe a change in a few points in IQ, for example, may not be relevant on a personal basis, but on a population basis, that may have a tremendous impact and an opportunity for an intervention and a reduction in exposure, if that's what is causing it. So again, I cannot speak of how relevant those just numbers that Jim shared are within the context of the data that you presented, but if they make a difference on a population basis, I think that is important enough.
Thank you.
Want to add anything else regarding just the strength of evidence that currently
just real quick.
exists?
I mean, we all know, and I think we all appreciate, ozone is an incredibly reactive chemical. And I mean, I just know this from our own studies. It's not going to stick around as ozone very much as soon as it hits any biomolecule. It'll react and transform that biomolecule to something else that we may or may not be able to measure. So we're always measuring surrogates. But there are, real ozone reaction products that may actually be a better marker for or direct ozonized biomolecules. That might be even a stronger way to measure the impact. But it goes without saying. I mean, 10 ppb ozone is going to be still a very reactive chemical that will interact with any biomolecule.
Lots of questions.
Hi, my name is Nadine Bordois. I'm an assistant professor at the University of British Columbia. And I have a question about how we look at ozone health effects in particular. So as an atmospheric chemist, what's so unique about ozone, it's that it's a secondary pollutant, right? It needs the VOCs to be there and the NOx and the light to form the ozone. But in the lab, we have ozone generators, we have mercury lamps, and so we can do ozone-only experiments. But in the real ambient environment, that's not the case. And so I wanted to know if you could speak to the role of the matrix and how important is the VOCs and the NOx present when there is ozone for these human studies, for example.
I think so probably there is no outdoor air pollution epidemiologist in the room. But if you look into the literature for 20 years, whatever the outdoor PM 2.5 ozone NO2 kind of health effects. The ozone many times come in to surprise people, not surprise anymore because you see more and more, but to puzzle people because many times you see those protective effects. And the large children's health study in Southern California depends on the way how you analyze them, isolate people. But in many cases, you run a model, you will see that PM 2.5, a lung function, there is a positive, negative, adverse relationship, and the ozone will be beneficial. And then you do the two pollutant model, adjust them, and sometimes the seemingly of beneficial effects disappear, sometimes don't, because you can't adjust that. So, but that's somehow people, always say, oh, because we see this because the ozone at PM 2.5 are strongly negatively correlated. When wintertime, ozone is low, PM is high, you see stronger effects. In the summertime, it's reverse, that sort of. So I think the literature stay in that way. If you look at read, 10 papers, ozone showed that kind of weird, unexpected thing. People would just say, it's the It's just the methods kind of thing. But now I think this work will actually point it to the more biologically relevant kind of thinking. Is ozone is not ozone. It's not just O3 when people inhale, right? It's the mixture, it's the reaction products, all that kind of things. So what is the best thing to actually measure? It's probably, we did this ozone loss. In those data sets appears to be showing more consistent thing with the biomarkers, limited number of biomarkers we look at it. But maybe there's better proxy, whatever, or what is the underlying physics, chemistry determine that exposure mixture? I think that's really need people in this room to figure it out. It's not the NIH supported investigators, they're biologists. They would never pay attention to these details.
So just to follow up on that, yes, and getting something like that funded through NIH is an uphill battle. So I think what you're speaking to also is the studies and the health effects studies we get from very controlled exposure chamber studies, which we do, and I know you do as well, versus what happens in the real world. And there is a discrepancy at times. Like we cannot reproduce what the epidemiological data shows us. Completely agree with you. And I think it also, again, sort of underscores the gap of looking at what you said, one chemical at a time. We cannot do that. So I think a better approach would be to take advantage of the mess that's out there in terms of the mixture. It is a scary mess out there, but maybe taking advantage of computational approaches where you're looking at patterns within the mixture that are correlated with patterns in biological responses. And while it is not a clear causality, the fact that they're migrating together in the same pattern indicates that they're somehow associated. So you can understand sort of chemical modifiers of biological responses. Ozone could be one of them, but ozone is so complex that it may just be a proxy for something else. So, going away from the sort of individual chemicals and doing health effects, I think is where we need to go.
Yeah, it's super interesting. So I guess as an experimentalist, there's like different sets of experiments to do, just the ozone only experiments, but then the ozone and the NOx, and then the ozone, the NOx, and the VOC. And then, okay, thank you.
My name's Joe Hughes. I'm with IAQ Radio, and I appreciate everybody's presentations today. I think one comment first is that for those in the field that do indoor air quality investigations, that's pretty much who I work with here. There seems to be a lot of opportunities that maybe we're missing. For instance, with the wildfire discussion earlier. I would love to have known not only that using a filter, an air filter is going to reduce these, but I also would love to have known, number one, how do I demarcate areas that have been impacted by wildfire smoke or any kind of smoke? Okay, what's the best way of doing that? Because that's a big controversial thing in the industry now. Is it a wipe sample? Is it something else? So if that could have been built into that research at the time, and the second thing is, great to know that the air filters clean the air, but what about the actual, how do they interact with actual cleaning that we do in the indoor environment? So if we clean that area and add an air filter, is that going to make it even better? Or do we not need the air filter? Can we just ventilate the room? So those types of things I think could be built into some of these studies that are going on. I don't know if it's a funding issue. It's kind of tough to get funding for different things, but I think industry would be willing to work with you on those things, volunteer time, and maybe even bring in some money from certain groups. The second thing I'd like to ask this group in particular is, right now we pretty much measure, some total VOCs, usually with a PID. We do temperature, relative humidity, a lot of times carbon monoxide, carbon dioxide, particle counts. We're always looking for moisture levels. all the things that you have been working on here, is there one exposure in particular that we don't look for that maybe you would recommend we do? Like, I noticed ammonia was elevated quite a bit in the indoor environment. And that's another thing. As a practitioner, I think of it as, okay, when you help to remove ammonia from surfaces, I think a lot of people in the room think that's bad. To me, that's good, because I'm going to remove it from those surfaces and then ventilate it out of the house. So what would you have me look at? Should I be looking at ammonia more often? Should I be looking at acrolein? What is the one that we know has some health effect for the people in these buildings?
Just the simply, we all sort of say, oh, I don't know. The thing is, we really don't have a health evidence to see, is this a mixture? I mean, ammonia or total VOC, I pretty much know that is not a very indicator for health. But anyway, I think lots of really to have like recommendation, for example, formaldehyde, because formaldehyde has a tons of solid literature to support that it is a bad compound, right? Other stuff, I don't know. I think we don't have evidence, scientific.
And do we have a way of measuring that somewhat inexpensively? That's the other problem we run into. No. Okay.
The only other class of compounds, not chemicals, compounds, that I didn't hear much about in the session this morning is biologicals. So spores, fungi, bacterial biologicals. So that obviously we know those have health effects. We know those. So that's the only sort of class that I've not seen in some of the presentations this morning, and that could be measured.
Thank you.
Hi, I'm William Fay. I'm a student at the University of Toronto, and I want to talk a little or ask you a little bit more about those mixtures of chemical compounds. And I'm coming at this from an SVOC perspective. We work on transformations of these compounds, and we can find that there's this explosion of chemical complexity as you react them away with ozone with other species, and adding that to the mixture of hundreds or thousands of SVOCs indoors, along with spores, allergens, co-exposure to ozone. How can we as indoor air chemists help you and help people out there to understand how to reduce these exposures, or understand what we need to really be caring about in the face of such a huge, sometimes feeling intractable problem of co-exposure there?
You would like to take that first?
I know it's a broad question.
I'll try. We need to take baby steps, and because the complexity is huge. And I think that it depends on really exactly what you're looking for. So you need to formulate what is your end goal, and then just say, okay, this is what I'm trying to do. And then try to develop the tools or identify the tools that are going to help you address that question or questions. So if you are interested in some type of regulation, so to speak, at least in the United States, is very chemical based. So you're going to have quantitative information for a particular chemical. So you're going to have targeted methods to look at one particular compound. If on the other hand, you're interested, and that could help you in just somebody saying, this compound shouldn't be used, and then it can be removed from commerce or whatever the regulation is supposed to be. If you're interested in looking more at the exposure, at the understanding what are we exposed to. Now, there are tools, including artificial intelligence, including non-targeted methods based on mass spectrometry that can give you a very good idea of what is in the environment, could be in the air, could be in the water, could be in wipe samples, could be in silicone wristbands, it could be in blood or urine. So it again is going to depend on what your study is going to be for. So there are more tools than perhaps we can, I mean, and that I'm certainly familiar with. At the same time, the more tools you're going to use and the more people you're going to involve, the more expensive is going to be your study and larger is going to be, and perhaps it's going to take much longer in finding the answers that you want. So again, I would just say, like everything in life, I would like to have it done yesterday, but it just, everything kind of takes, it takes time. I mean, when we say additional research is needed, some people would say, they always say the same thing, but in truth, research moves much slowly, and much more slowly than any one of us in this room would want.
Are there you'd like to add?
Thank you very much.
So probably an extension to that. So thinking about, there was mentioned before about indoor air quality standards. And what are some contaminants and chemicals that you see that would be, that there is evidence to suggest that there should be standards for? What is required to be able to develop these standards in developing policy moving forward?
For indoor air quality standards, I mean, we have obviously all of the things that we learned about this morning of just sort of like a regular sort of stagnant house. But I think for indoor air quality standards, what has not been discussed is air fresheners and like cleaning products. I know we're going to be hearing about later, but air fresheners, it's pumpkin season, right? So, and everything smells like cinnamon right now. And we do know that the chemical that conveys this sort of smell, cinnamaldehyde, does have health effects. We actually studied it in my lab. So, maybe indoor standards or indoor air quality standards should actually have, like, maybe start with like the big one, which is air fresheners and all of these sort of scented products, because they're, from the SVOCs, they're going to be creating a huge influx of chemicals. So maybe starting with something big. I don't know. But I do like the idea of creating indoor air quality standards.
A product related control as opposed to.
I think that's maybe because those are going to be big ones. Those are going to be very big chemical influx into the indoor air. Again, I'm not a chemist, but considering all of the things that I learned this morning and last night, I'm just sort of, now completely scared of air fresheners, because compared to what you guys can measure with just a regular house, I'm thinking like if you just do like one Glade press, it's just going to create havoc with all the measurements. So maybe starting with something like that. And they're a consumer product, so they're not controlled from a health effects point. They're more controlled from a dermal risk or like eating it or things like that, not from an inhalational risk.
Except to say that probably something that could resonate very well with the public. And then it's because if you go and just throw a name of a chemical, then people say, what? I say I'm a chemist and everybody thinks like the person with that white coat and crazy hair. And those things bubbling. So, if we just talk about something that people can understand and they just say, like this may have some advantage, or why are you using it? So it's really absolutely necessary. So, and it goes to the point as to, like, again, a lot of things are marketing, but do you really need the air fresh? Do you need that? Why do you need that? So if it's not absolutely necessary, then maybe we can just live without it.
A couple short questions as we'll need to wrap up.
Sounds good. My name is Ben. I'm at the University of Texas at Austin. In Austin right now, there's kind of a boom in some builders who are styling themselves as building scientists. And one of their big things is energy in buildings, of course, climate change and that sort of thing. But one of the big strategies for keeping the heat in where it needs to be, or the cool out, or whatever, is open cell spray foam with lots and lots of flame retardants. have you seen a lot of flame retardants starting to show up in people's in testing from the CDC?
Yes. So we have been measuring PBDs, those are the brominated diphenyl ethers, and we measure those in blood because they tend to persist in the body. We have evidence that their exposure to these chemicals. These have been discontinued their use in the United States starting in the mid-2000s until the late 2010s. So we do see levels that appear to be going down. At the same time, those brominated diphenyl ethers have been replaced with some other type of chemicals, so like organophosphates, and some of them are the chlorinated organophosphate that can be plasticized or also used as flame retardants. The difference with those is that they tend to not persist in the body, so they're just after the exposure has occurred, then they stay in the body for a few hours. We tend to measure those in the urine, but it's very evident that exposure to these chemicals, that we are exposed to these chemicals. Also, just think that flame retardants are in the carpet that we have, in the foam on everywhere that we're sitting. And I don't know about you, but couches, then you don't buy a couch and you get rid of it. So is again something that you mentioned earlier today, that then chemicals that may stay in the indoor environment for longer because they're going to have longer resident time, because then they're just going to stay in there. They may be off gas. They may just, in some cases, may attach to particulates, and then they're just going to be, again, recirculating in the home. But yes, there is evidence of exposure to some of these chemicals, at least.
Wrap up with one final question.
I'll be very brief. I'm Lou Radonovich with the National Institute for Occupational Safety and Health. I want to thank the conference organizers for including a panel about human health and chemistry meeting. I just want to advocate for large-scale studies that include both engineering data and human health data. Oftentimes in the literature, what we see are engineering studies with engineering data, and in clinical journals, human health studies with clinical indicators. Rarely do they come together. These studies are very expensive, and they take a long time to do. So I would advocate for public-private partnerships to fund large-scale studies that move the needle far further forward.
NIOSH and CDC is probably the only funding agency that would support this sort of convergence of the engineering and the health. I've tried with NIH. The reviewers are all biologists, and unless you have a knockout mouse on there, it's never going to go anywhere. So there's NIOSH does it, but not many others.
Is largely for occupational exposures. Right. So they would have to be a component in the occupation. And I don't know how much money they would be giving. Again, we get money to do our research. We actually do not give that much money out, I should say, just to start with.
Well, that's a wonderful comment to end on. And thank you so much for all of your insights. And thank you all for all of your questions.